The last section of this chapter on kinetics is talking about mechanisms, and also we're going to introduce the vocabulary of intermediates and catalysts. So when we talk about mechanisms, what we mean is that it turns out very few reactions happen in one step. Most of them happen in a series of very small reactions involving just one or two particles, maybe three particles. And if we think about that, like that means that how unlikely would it be that 3 or 4 big reactants all happen to like collide and react all simultaneously. So it tends to happen in steps. Each of these steps is going to be called an elementary step of the reaction, and the mechanism is the series of steps. So, and it turns out this has, understanding the mechanism of a reaction has great implications for understanding how to control that reaction. So in biochemistry, this is a really important thing. If we understand the mechanism, we can kind of understand the metabolic cycles of how things are being processed in the body, and it helps us to figure out what we need to do to improve regulation when things are going wrong. So the mechanism is very valuable information. It can help us in a synthetic reaction to make it better, to be able to improve our yields, and to, if we're trying to create a product on purpose, we really have a lot of information. So mechanisms is a big deal. Okay, so the series of these individual steps is called the mechanism, and each step of individual step is called an elementary step. Now, if we know the rate law of the reaction, it helps us, which we just looked in the last section, how I can find out the observed rate law for the reaction. It helps us to understand the mechanism. Let's go into a little more detail. All right, so this would be a particular reaction that could happen in 2 steps. So here I have hydrogen gas and iodine chloride. 2 molecules of that react to form. So this would be 3 molecules reacting. There's 3 molecules in total. Probably not going to happen in one step. Forms 2 hydrochloric acid, hydrogen chloride molecules and iodine. So it turns out a mechanism could be hydrogen first reacts with 1 molecule of ICl, so that's only 2 particles, and then it forms an HCl, and then as the other product is HI, and then that HI goes on and it reacts with the second molecule of ICl and makes another HCl plus I2. So overall, we see that that this HI would be made but then used up here, so it goes away. And I overall used H2 and 2 ICLs. I end up with 2 HCl's and I end up with I2. So this could be a possibility of how this overall reaction occurs. So more vocabulary. Molecularity is the number of reactant particles in an elementary step. So in both of those steps, in the last one, each individual step only had 2 molecules reacting. So that would be considered a bimolecular step. So a unimolecular step involves 1 particle. So sometimes we have 1 particle that just decides it's going to break apart. If it's kind of high energy and unstable, I can just have one thing that decides it's going to break apart. It doesn't collide with another particle, and that would be a unimolecular step. A bimolecular step is fairly common, and that one involves 2 particles. They could be the same kind of particles, so it could be an oxygen and another oxygen, or it could be an HCl and an ICl, or H2 and an ICl. So it could be the same or different kinds of particles, but there's 2 of them that are interacting. And in a termolecular, which is, again, starting to be rare, involves 3 particles. So all 3 particles that had to simultaneously collide and interact. And so they're fairly rare. And we're not going to see tetramolecular, like termolecular is rare enough. So, and I could get these from adding up the coefficients on the reactant side of the step, and because the number of particles is equal to the sum of the coefficients. Okay, here's a problem. There is no way to look at a reaction and to actually know if a reaction is an elementary step in a mechanism. I can't tell. And I can't tell, therefore, that this is the real correct mechanism. All I can do is I can propose a mechanism with a set of elementary steps that add up to the overall reaction. And I predict the rate law of the mechanism. And then I experimentally measure the mechanism rate law, the rate law of that reaction. If the rate law that I observe is equal to the rate law for the mechanism, it's at least possible. But if the rate law observed is not matching the rate law I'd expect for the mechanism, then that mechanism is not the mechanism. So all I can do is rule out possibilities and get down to a list of possible mechanisms. And this is kind of tedious work working in kinetics, but it's fairly important. So more information. If it is an elementary step, and as I just said, there's no way to really tell. So we have to and we can only do this for elementary steps. It turns out that the rate law for an elementary step can be deduced from the molecularity of that step. The order with respect to a reactant in an elementary step is the number of particles of that reactant. So it's its coefficient. But this is only true, and I keep stating this again and again. We can only say that the order with respect to a reactant is its coefficient if the reaction we're considering is an elementary step. You can't do it with the stuff that we've been doing so far where we had multi-step reactions. It doesn't work. So this is only done when we're dealing with mechanisms. And people will make that mistake a lot instead of using experimental evidence, and it goes badly. So once you get to this point, remember this is only when we're doing mechanisms. If we have an elementary step, so if this is an elementary step, then the rate would be K times concentration of H2. Since there's just one of them, its order would be 1. And concentration of ICl, since there's only one of them, so these orders are 1. Same thing in the second reaction. It's a different rate, so it's a different step. So we use K2 just to identify the 1 and the 2 are now talking about the first step and the second step. And again, both of these have one HI particle and one ICl particle, so it'd be, both of them would have an order of 1. If it was an ICl hitting an ICl, it'd be ICl to the second power. Okay, so this is half of the story of how do I predict the rate law for a mechanism. The next part is about the rate determining step. Okay, so for instance, if I look at these, this has a molecular rate of 1, there's just one particle, and the rate law would K to the concentration of A. If I come down here, there's 3 particles, they're all the same, it's A, so it'd be K A to the cubed power. Again, we've only been dealing with powers of like 0, 1, and 2. A plus B would be first order in A, first order in B. But A plus A would be second order in A. So this would be writing a rate law, but again, we only do this if it's an elementary step and if we're doing mechanisms. All right, so now let's talk a little bit about the rate determining step. In most mechanisms, the rate determining step is the step with the slowest rate. Pretty much the only ones we're going to do. We're going to assume that the slow step in the reaction is the rate determining step, which makes sense. Anything that I did with production, everything gets slowed down by what is the slowest step. It doesn't matter how fast the early or late or stage steps are. Whatever step is the step that takes the slowest is going to determine the overall how long it takes for the whole process. So the rate law of the rate determining step would be the same as the rate law of the overall reaction. So I have to determine what's the rate determining step of my proposed mechanism. I have to look at what would its rate law be, and then I have to compare that to the observed experimental rate law for the reaction. And just to remember that the slowest step can be recognized on a reaction profile as the one with the largest activation energy. The higher the activation energy, the slower that step. As an analogy, so if we are looking for a proposed mechanism, I need 2 criteria to be true. The elementary steps must sum to the overall balanced chemical reaction. In other words, I've got a reaction, my individual steps have to start with the same reactants and end with the same products overall in the same quantities. So, and I can add them just like I'm adding like algebra expressions. I can add them together in the same way. And then the rate law predicted by the rate determining step of the mechanism has to match the experimentally observed rate law. If both of those things are true, at least then what I can say is I have a valid mechanism. It's not the correct mechanism. I don't know that it's the correct mechanism. I can't actually watch the molecules reacting, and I will never know. but I can say I have a mechanism that is consistent. It's a valid mechanism for the observed reaction. And that's still very helpful for us. If it's not consistent, if one of these things is not true, then I know, well, that's not the mechanism. So that's how we begin. Let's go through some examples. Okay, so I'm talking about NO2 and CO. The observed rate turns out to be second order only in NO2. So a series of steps that would get me there is a two-step reaction which an NO2 and another NO2 collide, make NO3 and NO. Then the NO3 that was made reacts with the CO and makes NO2 and CO2. And so in this case, the NO2 that got used up got regenerated, one of them did, and one of them was reactant, and then the carbon monoxide got reacted in the second step. So overall, if I add these NO2, note that I have two NO2s on the left, but I have one NO2 on the right. So this one and this one cancel out, and I just have NO2. And then this NO3 was made on this side, and it was reacted this side, so it cancels out. So all I have left on the reactant side is CO. And on the product side, again, these two have been canceled out, so I just have NO and CO2. Now also, suppose, right, I have two steps. This could be a good set of steps, but then which one is the rate determining step? So the proposed mechanism is that the first step is the slow mechanism. So let's see if that would pan out. So again, the sum of the mechanism steps adds up to the overall observed reaction. So this is a possible mechanism. Step 2, I'm looking for that the step 1 is the slow step, so it's the rate determining step. And if I were looking at the rate law for the first set, it is K times NO2 squared because it's the same particle, so it's really 2 NO2. I could rewrite this as 2 NO2 makes NO3 plus NO. So this would be NO2 squared. And for the second elementary step, it'd be NO3 times CO. Well, note that the observed rate was K NO2 to the second order. So the step 1 matches the observed rate law. So if I propose that that's the rate determining step, then this mechanism would be valid. If I were going to draw it out as a reaction profile, it might look something like this. I have my reactants. Remember, my rate determining step would be my higher activation energy. So I have a big barrier for the first step because that's the slow step, and then a smaller barrier for the second step, and then overall I make my products. Now, as far as the exothermicity or endothermicity, I'd have to have that information otherwise. But this would be a two-step process. And so I would expect, because this is higher activation energy, it would be the smaller K rate constant and the slower reaction step. Okay, so it gets a little bit uglier if the second or a later step in the reaction is an initial step. I got to do a little bit more math to get my observed rate law, or my mechanism rate law. So if you have a mechanism with a fast initial step, that is not the rate determining step, but it may contain intermediates. Intermediates are things that then get made in an early step, but then react in a later step. So they end up, they're not there at the beginning and they're not there at the end. They're really not reactants. They're just made along the way. And when we have those, the problem with it is because they're not initial reactants, I can't make the rate law based off of that. The rate law has to be based off of actual reactants in the overall equation. So since they're not reactants, the rate law will include intermediates in it, and that's not going to ever match the observed rate. So then I have to use some little tricks to figure out what would be the concentration of the intermediate that's in the rate determining step rate law based off of actual reactants. And the way that I do that is that if I have a fast reaction, I can assume it's in equilibrium. Right now this is all garbage talk for you, but next chapter is equilibrium, and at the end of next chapter it will make more sense. If I have a reaction in equilibrium, it turns out that the forward rate is equal to the back rate. So I'm going to write the rate law of the forward direction and then the rate law of the reverse direction. I'm going to set them equal to each other, and I'm going to solve for the concentration of the intermediate that's in the rate determining step rate law. So it's a little bit tricky, but and And when we finish doing all this algebra, there's going to be multiple steps there. So the K will actually be like a K2 times a K1 divided by a K negative 1. It will be kind of like a product of rate constants. But a constant times a constant divided by a constant is still a constant. So sometimes they change the subscript of the K to indicate that it's actually into several Ks. It doesn't even matter. So let's look at an example to see if this makes a little bit more sense when we look at a particular problem. So in this case, I have a 3-step mechanism proposed. Two NO2s break down and make N2O2, and then hydrogen gas reacts with that NO2 that was produced. So NO2 is an intermediate, right? It's made in an early step and reacted in a later step. And that makes water and N2O, and then H2 and the N2O from this step. So note that N2O is also an intermediate. It's made in the second step but reacted away in the third step. Makes water plus nitrogen. So I end up with 2NO, 2 H2s. These two are intermediates. They're not going to be seen in the final formula. Makes 2 waters and N2, because these two also will not appear. So if you add them all up and cancel things, you'd see that these 3 steps sum up to here. 2NO plus 2H2 makes 2 water plus N2. So the proposed mechanism says that the second step is the slow step. So if I write the rate law for the second step, it would be K2 times H2 gas times N2O2. The problem is that doesn't match what we observed because N2O2 is an intermediate. So I now need to say, but can I rewrite N2O2 concentration in terms of NO and H2? And the way that I do it is I go to the fast earlier step. Again, if it's a fast step, I can assume it's in equilibrium. And again, I know you haven't seen these arrows yet, but when I have these double arrows, that means in equilibrium. And I have a forward reaction. I'll call that, since this is the first step, I'll call the forward reaction has a rate constant of K1. And the reverse reaction has the rate constant of K negative 1, negative being the reverse reaction. That's just the sort of notation that we tend to use. You could use whatever you want. So I now say that this forward rate has to equal the backwards rate. Well, the forward rate is, the forward rate would be K1. Oh, here we have up here. So this forward direction would be K1 times NO concentration squared, right? K1 NO concentration squared. The reverse step would be K negative 1 times concentration of N2O2. That's here on the right-hand side. I set them equal to each other because the idea of equilibrium is that these two rates are equal. And I rearrange it to solve for N2O2 because that's the intermediate I want to replace in this rate determining step. And I get K1 over K negative 1 times NO2 squared. Now I plug this back into my rate determining step, K2, H2, N2O2. I plug the N2O2 in here and rearrange, and I get that K2 times K1 over K negative 1, so all the K's are together, is H2 times, now I have NO2 squared, and here's the H2 on the other side, but I just reordered them. And so what I see is that I get the rate is some K. Again, this K is really K2 times K1 to K negative 1, but it's still a constant, so it's a K times NO squared times H2, which is the observed rate. So this mechanism does match the observed rate law, but to see that it matched, I had to do this intermediate step. They call this the steady state approximation sometimes. An earlier fast step, I assume it's at steady state or in equilibrium. I set the rate laws for the forward and the reverse reaction equal to each other, solve for the concentration of the intermediate, plug it into the rate law for the rate determining step to get a rate law that's in terms of the original reactants of the overall reaction. So let's define another thing. We've defined intermediates, right? They're ones that are produced in an early step and used in a later step. A similar but reverse thing is catalysts. They're present at the beginning, they're present at the end, but they don't get consumed in the reaction. One way that can happen is that they're present at the start of the reaction, get used up, but then get regenerated in a later step. And so I end up having things, so these are catalysts, and you have heard of catalysts before, and catalysts tend to speed up a reaction. And the way that they speed them up is by providing an alternate mechanism with multiple steps, in which case the catalyst is used and regenerated. So we see in this catalyzed pathway, I have a lower activation energy for each of my steps, which means there'll be faster rates, so I end up with a faster process. So it's a different pathway. And so again, I would recognize a catalyst. So in this case, I have no catalyst. I have oxygen, ozone plus atomic oxygen makes two O2 molecules. And this is a very slow process. But look what happens if this catalyst chlorine, or it's a monatomic chlorine, reacts with ozone. And by the way, we think that this happens up in the upper atmosphere. So this is one of those ozone depleting reactions, that this monatomic chlorine, which gets produced by photolysis of chlorine chemicals in the atmosphere, can react with the ozone to make one oxygen and this ClO intermediate. And then the ClO intermediate reacts with the singlet oxygen to make another oxygen gas, and it regenerates this monatomic chlorine. So this monatomic chlorine was there at the beginning, and it's reacted earlier, produced later. So it's there at the beginning, it's there at the end, but it cancels out of the overall reaction. It's the catalyst. The ClO that gets generated in an early step but used in a later step is the intermediate. So I see a catalyst, I see an intermediate, and this one happens significantly faster. This slow step has a lower activation energy and happens much faster than this one-step slow step process. So that's how catalysts act. Now, there's a couple kinds of catalysts. So again, what they are doing is that they speed it up, but it turns out I can have catalysts, same thing, but I have some high activation step where it actually slows down the reaction. And we see this in biochemistry sometimes, that they could be, there are such things as negative catalysts that slow down a reaction. They're a little bit more rare. The typical, they're going to speed up a reaction. And I have two kinds. I have homogeneous. Homogeneous means same type. So that would mean they're in the same phase. So I have a gas, like in that last one, we had a chlorine gas atom and a ozone gas molecule. So they're both gases and they're reacting with each other. That would be a homogeneous catalyst. But we also see a lot of times these heterogeneous catalysts. And a heterogeneous catalyst is one where it's in a different phase. And we see a lot of times we'll have a solid state catalyst. And what's usually going on is reaction, that it helps a reaction to happen on its surface, and so that the reactants are in the space above, either liquid or gas, above the catalyst, and then they sit on the surface, and that helps position them so that they can react more quickly with less activation energy. And so we see that, so one example is the platinum surfaces in catalytic converters that will decompose the carbon monoxide gas that's produced, or sometimes unburnt hydrocarbons, and it decomposes them into more safe products. And so that catalyst, that platinum catalyst, is a heterogeneous catalyst.